Let's discuss the concept of quadrature phase shift scheme. This is also a modulation scheme. In QPSK, let dk represents the incoming bits of sequence. Then we apply a bit splitter. The work of bit splitter is to split the incoming bits into two sub bits of half the rate if RB is the rate at which dk, the source is generating the bits dk. So these bits are called subsequence of bits dki and dkq. The rate of this will become half of the rate of this. Next we apply polar coding. And then so this upper branch is similar to BPSK performed over DKI. Similarly, for the lower branch, we will again apply polar line coding. And then it gets the multiplied with minus a sine 2 pi fct. So this is the difference, that we are performing this multiplication of a cos 2 pi fct for the upper branch, and we are multiplying a sinusoidal signal in the lower branch. What we have seen in BASK or BPSK, we have used, or we have multiplied only, or we have modulated the carrier cos 2 pi cos 2 pi fct, right, if you remember. And in BFSK we have used cos 2 pi f1t and cos 2 pi f2t, but we have not used cosine as well as sine carrier simultaneously, and that is why it is called quadrature, since both the carriers are in quadrature. And then the whatever output of the first branch, we represent it with SIT and SQT. The upper branch is known as in phase channel, and the lower branch is a quadrature phase, because this is in quadrature phase. Or you can also generate a sinusoidal signal. If this is cosine, then you apply a pi by 2 phase shift, you will get a sinusoidal current. So this is your ST, which is summation of in phase signal and the out phase, quadrature phase modulated signal, and this is our effective QPSK signal. Of course, before transmitting this signal, we pass it through the band pass filter. We pass it through the band pass filter so that it does not interfere with the other signals. For example, there is one more transmitter which is transmitting nearby, so this does not interfere with the signal of other transmitter. Therefore, we put a band pass filter. This band pass filter makes sure that the main lobe of this power spectral density, if we plot power spectral density of QPSK, at this main lobe of this passes through. Now we'll discuss how to draw the constellation for ST. ST is our QPSK signal. It is now very clear that what is quadrature, why do we call it quadrature, and the phase shift king, why do we call it phase shift king. It will become evident shortly. So first let's plot the, in order to see that, first plot the constellation diagram of this. So for the constellation diagram, what do we need? We need the basis functions which are required to fully represent all the possible e's. So for that, what we are going to do, we are going to find out basis function independently for in phase and quadrature phase signals first. So what are the possible choices of SIT? First, A cos of 2 pi FCT, and another is minus A sine 2 pi, sorry, minus A cos 2 pi FCT. So there are two possible in phase channel. We can call it SI1T and SI2T. So we need to find out the basis which is required to fully represent S1IT and S2IT. So as you can see that S2IT is minus S1IT, means S2IT can be represented in terms of S1IT, and therefore we need only one basis to represent these two signals. And if we represent that one basis by phi 1 IT, it will be, we can evaluate this as this, where E is the energy of your S1 IT. So let's evaluate energy of S1 IT. So equivalently your S1 IT is root E phi IT. So first what you have to find out, what is energy E, and then we will divide and we will find out the basis. So energy is A square, now you just square this term, and you have to integrate it between 0 to TB. Why? Because I told you that the bits which are going through the in phase channel is half the rate of the bits which are actually coming to the setup, QPSK setup, and therefore the bit duration of for this DKI will become double the bit duration for this. So if it is TB, it will become 2T. And I just here will clarify what bit splitter does. Example, so let us say that DK is 110110. So all the 0th, 2nd, 4th even number of bits will go to I channel, and the odd number of bits will go to the Q channel, and the duration will become double. Okay. So we were performing the, or we were evaluating or calculating the energy of the S1 IT signal. So S1 IT is A cos 2 pi of CT, therefore energy will become this, and since the duration of this pulse is this signal, so you can write duration is from 0 to 2 TB. A square 1 plus cos of 4 pi fct dt divided by 2. Though we have done it many times that any signal of type this, the energy is AC square into this value 2TB divided by 2. So just we are doing it again. A square, this is the first term, half, and we integrate 1, integration of 1 is t, so you just put 2TB, and the second term a square by t 0 to 2TB cos of 4 pi fct dt. So if your fc is if you remember, I told you what cos 4 pi fct can be written as a square by 2 0 to 2TB cos of 2 pi into 2 fct dt. It means the frequency of this signal is 2 times fc. So if 2 fc is such that, means in this is the 2TB duration and our frequency of signal is such that it repeats integer number of times between this 2TB. So if 2TB, so what would be the number of cycles? 1, 2, here I have taken 4 number of cycles in this duration. So this is the frequency. If let fc is the frequency of this signal, so 1 upon this will become 1 upon tc. Sorry. So if fc is the frequency of this signal, then this time duration is 1 over tc, the time during which, or you can just call it t, not 1 upon t, it's t. So t is 1 over frequency of this carrier, right? And we are calling that this t is k times the integer number of 2TB. Sorry. That 2TB is some integer number of nt, which is equivalently you can write that one over fc is 2TB, n over fc, sorry, n over 2fc is equal to 2TB, or fc is equal to n by 4 rb fc is equal to, or you can see like this, that frequency of this signal which you are getting 2fc must be integral multiple of this n times of integral multiple of this. So if we make sure this, where t is this quantity, this value, if we make sure this, that this happens, then integration, if we perform integration of this we'll confuse it again, so write tc here, and this is this quantity t. So in essence, if the carrier which you are integrating, sinusoidal or cosine signal which you are integrating, the frequency is integer multiple of 1 over t, or 1 over the integral which you are using, then if we plot this type of signal we will observe, means the cycle, number of cycles are complete, and therefore the positive part will be equal to the negative portion. If you see in one cycle, the positive portion and negative sequence are equal, and therefore the integration will turn out as 0, and therefore second term will become 0, and the energy of this signal is this. So this we have already seen, right, many times. Next, what we are going to do, that we have found out the phi 1 IT means basis for the to represent all the possible in phase signals. So this is what we have find out. So phi 1 IT is A cos 2 pi c fct, which is S1 IT, and divided by energy, which is A square TB square. Just make this square. So A, so this will become 1 over root TB cos of 2 pi fct, T between 0 to 8. And thus S1 IT can be represented, because our aim was to represent our all the possible in phase signals in terms of basis, so it will be this. Next we'll see, we'll perform the similar analysis for the quadrature phase signals. So what are the two possible quadrature phase signals? A sine 2 pi fct, or because for logic 1 just we have used minus a sine 2 pi fct. So whenever we transmit 1 we get minus a sine 2 pi fct. So this is S1 qt, this is S2 qt, the second possible signal which can come out of the Q branch is A sine 2 pi fct. Again we want to find out a basis, minimum number of orthonormal functions which are independent, right, linearly independent, to represent these two signals. So as you can easily see, and therefore only one basis is required, which is I am not again performing how to calculate energy of this signal. The steps are very similar, and the answer would be minus a sine 2 pi fc t divided by a square 2tb by 2 energy square, and the answer would be minus 1 over root tb sine 2 pi fct. And thus we can represent our quadrature signals in terms of, so S1 qt is root e phi qt, and S2 qt is minus root e, or F2 qt is minus of S1 qt, which is equal to root e phi qt. We have find out the, because our aim was to find the basis for ST, but we have independently find out the basis for SIT and SQT. Now you can write ST as, what are the possible, because we need to draw the constellation. Our aim was to draw the constellation for ST, or constellation for QPSK signal ST. So we need to find out what are the possible STs, what are the possible QPS signals. So S1T. So first, if you remember, ST is SIT and plus SQT. And there are two possibilities of SIT. Similarly for SQ, we have two possibilities. So there are, ST can be 4. ST consists of 4 possible QPSK signal. So S1IT plus S2IT, S1IT plus S1QT, just correct it, S1IT plus S2QT, S2IT plus S1QT, S2IT plus S2QT. And if you convert, just write S1 as well as S2Q in terms of their basis, you will see that root E phi IT plus root E phi QT. This is root E phi IT. This is minus root E phi QT. It will represent our S1IT plus S2QT. You will get this type of, when we transmit 1, 0, right? This we get when we transmit 1, 1. It means when DI is 1 and DQ is 0. So these are the DI DQ. Corresponding to that, we get this S1T, this S2T, and this S3T is S2IT, means minus root E phi IT, and S1QT is, S1QT, if you remember, is root E phi, sorry, this I have to change, root E phi QT, and this is S2QT is minus, so just I have made a mistake, so you need to correct it. This corresponds to 1, 0, this corresponds to 1, 1. minus root e phi I t. S1 qt is root e phi qt, which is for 0 1, and S2 it is minus root e phi it, and S2 qt is minus root e phi qt. Please once verify all of this. So now we have these possible signals. So constellation for xt would be constellation for QPSK. QPSK constellation is a pictorial or graphical representation of all the possible signals which are coming out of the transmitter and the basis, and this in terms of basis phi it. So this is a two-dimensional. So now you can write this is root e times phi 1 t. First I am plotting this S2t, or you can make it S1t, and you can make it as S2t, this as S3t. So this is the representation for S1t. What is the distance? 2 root e, root square root of and this represents our S1t, this represents S2t, this corresponds to 1 1, logic 1 1, when decay is 1 1 we get this. S2t 0 1 means minus root e comma root e, then we have S3t, S3t, so make S3t as this. Just we are changing the nomenclature, you can keep whatever you like. S3t is minus root e comma minus root e, and S4t is root e comma minus root e. So now you can see all these signals has equal distance from the origin. It means amplitude of these signals are same, only the phase is varying. That is why it is called phase shifting. It will further become clear when we have polar representation of ST. So let's try to see ST. ST is what? QPSK signal in form of polar representation. So what was a QPSK ST? ST can be, if you just go to the very basic starting, it can be a cos 2 pi f ct minus a sin 2 pi f ct. So a cos 2 pi f ct minus a sin 2 pi f ct. If we transmit 1 comma 1, then a cos 2 pi f ct plus a sin 2 pi f ct. If we transmit 1 comma 0, minus a cos 2 pi f ct plus a sin 2 pi f ct. If we transmit 0 0, and minus a cos 2 pi f ct minus a sin 2 pi f ct. If we transmit 0 1. So you can write, you just take any signal and multiply it with the root 2. What you will have? Cos of 2 pi f ct 1 by root 2 is minus sin 2 pi f ct 1 by root 2, and this you remember that it is cos 45 or cos pi by 4, and this is sin pi by 4. So you can apply the trigonometrical expression that cos A plus B is cos A into cos B minus sin A sin B, and we will get cos of 2 pi FCT minus pi by, sorry, plus pi by 4, because we have minus here. Similarly, if you perform this type of, so you can write our second signal as or just take this as second signal. Sorry, it's minus minus, so there is something, yeah, 0 1. Okay, yeah, so just try to write what we will get for this. A cos root 2a cos of 2 pi FCT, since there is a minus sign difference only, this signal can be represented as root 2a cosine of 2 pi FCT minus pi by 4, right? So this signal is here, this signal will be minus pi by 4, and similarly you can put this is minus of this, so you can write minus root 2a cos of 2 pi FCT plus pi by 4, so it will be since this is 1 1, this is corresponds to 1 0, this will correspond to 0 1, this will correspond to 0 0, so minus of this is this, so you have to just minus this, right? Similarly, the minus of this is this, so you can see that in polar form also you can represent your QPSK signal, and the best and the final answer we will write it like this. Though we have already plotted it, right? Yeah, we have already plotted it. So this is the constellation, but now you can view it as a, and another way you can see these 4 points, that theta 1, this can be represented as pi by 4 and root 2e, and this is 3 pi by 4, this is 5 pi by 4, this is, and this will be 7 pi by 4, right? So you can write your ST as effectively AC cos 2 pi FCT plus 2m minus 1 pi by 4, where m is 1 comma t comma 3 comma 4. So you can also visualize that your ST which are coming out of this transmitter will have this form, right? Just put m is equal to 1 here, you will get pi by 4, 2, you will get 3 pi by 4, 5 pi by 4 and 7 pi by 4. So one more, once we get the constellation, in the previous class we have seen how to read this constellation. So one important point you need to see here, that if you see that AC is root 2 times A, that is amplitude of the signal or which is coming out of the QPSK, or the QPSK amplitude of the QPSK signal. QPSK amplitude is root 2 times the amplitude of in phase and quadrature phase carrier. ठीक है. So just you have to remember this. And in the previous class we have seen that if we know the constellation diagram, what are the various information you can infer from this? What is the energy of each signal? So this is S1T, and energy of S1T would be, because we have not yet derived the energy of the QPSK signal. Energy of S1T would be, if we represent it by E1, it will be given as, I told you that it's a distance square, right? So 2 times E. And if you remember, E was energy of the in phase and quadrature phase signal. E was the energy of SIT as well as SQT, right? And this value was A square TB. Okay? E2 is also 2E, E3 is. Of course it should be, because ST is summation of SIT and SQT. Therefore the energy of ST or the QPSK must be summation of energies of the in phase signal as well as the quadrature phase channel. So again, if all signals are equiprobable, means zeros and ones which are coming to this is equiprobable. So of course 0 1 1 0 1 1 would also be equiprobable, right? Because this represents 1 1. So if probability of occurrence of 1 is half, probability of occurrence of 1 is also half, the probability of occurrence of 1 1 will become 1 by 4. So average energy for the equiprobable case is 1 by 4 summation of all E1, E2, E3, E4. So it is 8E, and it will be same as E signal, right? Thank you.